Hello, here we're going to continue on with probability. One type of probability is called experimental probability. And what you'll see with probability is that sometimes they'll put this P right there, and that stands for probability, and then in the parentheses, you'll say what the event is or what you're looking for. So what we're going to look at here is a basketball player attempted 24 shots and made 13. Find the experimental probability the player will make the next shot that she attempts. So this one's going to be the probability of a made shot. And so the way to calculate this is just like any other type of probability, to where the probability is the number of times the event occurs divided by the number of trials. This is what we'll use on all the different examples. So for this one, they'd attempted 24 shots, so that's going to be our denominator, and they had made 13. So the probability that they're going to make the next shot from an experimental probability standpoint is 0.54. And if we multiply that by 100 to turn it into a percent, we're at 54%. Now, what experimental probability is all about is finding the probability of something that you cannot do technically. When someone's shooting a shot, there's all sorts of factors that come into play, such as fatigue. It doesn't specify if these are all free throws, to where it's kind of a safe environment to where you can repeat the process very easily. So what we use is called experimental probability, to where based on the data, it's our best guess on what the probability would be, but we can't classify it really more technically than that. And you can use experimental probability to come up with probability for things that you don't have a bunch of data on. For example, if you went into ceramics class and made your own clay dice, and say you tried to make it as balanced and possible and fair as you can, but say it's a little lumpy, and you wanted to find what the probability is of each side, when labeled 1 through 6, would come up as, you could find that by rolling it a whole bunch of times and then keeping track and figuring out how often certain sides came up. We wouldn't just want to say about your dice that the probability is 1/6 because we know it's not a perfectly made and balanced dice. So we can find what's called the experimental probability by rolling it a whole bunch of times and figuring out kind of what happens. And that would give us some sort of picture about what type of probabilities to expect. So experimental is when you have to do an experiment to find out what the probability is. It can be very reliable, especially if you do a lot of trials. Because if you had your dice, draw a cube here, and you had rolled it, let's say 1,000 times. And then from that 1,000 times, if you had kept track of how many times it landed on each number, you would then have a pretty good idea of what the probability is of it landing on a certain spot. So let's say, for example, when you rolled it 1,000 times, it was 160 times that it landed on a 1. Let's say 172 times it landed on 2. Say 175, 161, 157, and 175. You'd be able to come up with the experimental probability that it would land on the different sides. And we'd be able to do that by just putting, all of these over 1,000. And that could generate us the experimental probability of your different sides of your dice. And you'll see that it's not perfect. It's not perfectly balanced because we made the dice ourselves. But you can still use experimental probability to make some claims about how often or what percent something could happen at. So I'll finish labeling these here for us. All right. An outcome is a possible result of a situation or simulation. An event is any outcome or groups of outcomes. And then there's something called a sample space, which is all possible outcomes to an experiment. And so the probability of some event A, where n is the sample space, so sample space is going to be our denominator, and m is how many times the event occurs. So back in the mid-90s, the dream was to acquire a holographic Charizard, and there was no online services to really make this happen, so you just had to get it out of the actual pack. And each pack had 5 common cards, 3 uncommon cards, 1 rare card, and 1 random card. There were 102 different cards in the original packs. 32 of those were considered rare. So what we're about to look at is theoretical probability. Now, theoretical probability tells you, in a perfect world, what would happen, what's your chances of getting a Charizard in a perfect scenario. Now, we maybe have all experienced a scenario where you buy 100 packs and you still never get them, and that can certainly happen. Maybe your friend buys 1 pack only, and his very first pack, he got a Charizard. So anything can happen, but we're going to find the theoretical probability of getting one. So there are 32 rare cards, and in each pack you're going to get 1 of them. So just from that probability alone, you had a 0.03125 chance. So if we multiply that by 100, you have a 3.125% chance of getting a Charizard. But then there was also a second way of getting it too, because you also got 1 random card. So you got 1 random card. It could be another rare, could be a common, could be any of the other ones. And there was 102 possible cards that could be out of. So that one is 0.0098, and when we multiply that by 100, it's 0.98%. So if you combine those, which we're not really going to focus too much on adding probabilities, but I wanted to show you 2 different scenarios where we have different sample spaces, because this is the total number of rare cards. This is the total number of all cards. And both of these ones are representing the Charizard. So if we add those together, you have a 4.1% chance of getting a Charizard. So what that means theoretically is that if you bought 100 packs, that you should get about 4 Charizards. Is that a guarantee? No, because this is theoretical. You could buy 100 packs and not get any. You could buy 100 packs and get 10. But the theoretical probability, if you open 1 pack, is that you'd expect to get a Charizard 4% of the time. So theoretical probability is what you most are accustomed to when talking about probability. In a situation like this, to where a bucket contains 15 blue pins, 35 black pins, 40 red pins, you pick 1 pin at random, find each theoretical probability. Notice that they're using that notation there, such as P of black pin. So that's asking what's the probability of getting a black pin. And so what we'd have to do is work with the sample space and then the event that we want. So when we're trying to draw a black pin, we need to figure out, what's the total amount of pins in there? The sample space is going to be 90. So that's going to be our denominator. And then for the black pins, there's 35. So if we do 35 divided by 90, and you could simplify that fraction, but for the most part, we're going to want them as percents. We'll get 38.8% chance of drawing out a black pin, which should make sense because 30 would be 33%, a third of it. 35 is a little bit higher, so our 38% is a little bit higher. And you can do this with different events, blue pin or red pin. So it'd be 15 plus 40. So really you're looking at 55 out of 90 there. And when you do that, you get a 61.1% chance. You can do things as not a blue pin. And you could do that by either adding up the black and red pins. You could also take the sample space and subtract the 15 and do it that way too. Sometimes people think of it from that perspective. And when we do that, there's really 75 out of the 90 pins that we want, which gives us a high percentage of 83.3%. And then we want the probability of black pin or not a red pin. And so what we have to be careful of is as the events start to get more complicated, we have to pay a little bit more attention. Yes, our sample space is still 90, but here's what we'll have to do. We'll have to think hard about what it means to not get a red pin. Sometimes you can think about these and summarize it. So if we're thinking about black pin or not a red pin, really that just means we want a black pin or a blue pin, because there's only 3 options, right? So this is really, what about black and blue? Because if I draw a blue pin, it satisfies the not a red pin option. So sometimes it's helpful to think about what the event is really asking you before you go to calculate. So we have 15 blue pins plus 35 black pins. So we're looking at 50 out of 90. That's going to give us 55.5%. And all of that is theoretical, right? So like for this one, even though it's a really high percent, 83%, is there a chance that you still go in there and grab a blue pin as that remaining 17%? Yes, this is all theoretical probability. So theoretical is as simple as it seems. What's the probability of rolling a 5 on a die? There's one way to roll a 5 out of 6 options. What's the probability of rolling a sum of 5 on 2 dice? This one can sometimes fool people. If you play a lot of games, you might be familiar with rolling 2 dice and the possible outcomes. You can Google dice probability or 2 dice probability and you'll see a chart. The chart looks like this, to where it gets larger as you go up. 2, 3, 4, 5. And then it starts to scale back down. 7 is the most common number that you can get. And the roll 2, the only way to roll a 2 is to get 1 and 1. There's only one way of doing that. There's also only one way to get a 12, because it's 6 and 6. But for the other ones, to roll a 3, you could get a 1 and a 2. And it also counts the other direction, 2 plus 1. So there's 2 ways of getting that one. Same thing for 11. There's 5 plus 6 and 6 plus 5. So you could look up this chart, but what we're looking for is, what about rolling the sum of 5 of a dice? Well, there's 1 and 4, there's 4 and 1, there's and 3 and 2. So there's 4 ways of getting it. If you're curious about the 4, there's 1 and 3, 3 and 1, and 2 and 2 only counts once because you can't flip-flop it. So it actually makes an even distribution that goes up like this. 1, 2, 3, 4, 5, 6, and then it starts to scale back down. So for us, what's the probability of rolling a sum of 5 on 2 dice? Well, there's 4 ways of doing that, and if you add all of these numbers up, it ends up being 36. Now that's not a coincidence. That's because there's 6 sides on each dice. 6 times 6 is 36. So our sample space here is 36. And that gives us an 11.1% chance. So if you were playing Monopoly and you really needed a 5, you have almost a 1 out of 10, barely higher than 10% chance of getting that. And you can do theoretical probability with cards as well. What's the probability of drawing an 8 on a standard deck of cards? In a standard deck of cards, has 52 cards, so that's going to be our sample space. And there's actually 4 8s in the deck. So if you were really trying to draw an 8, 4 over 52 is a 7.6% chance. So that's theoretical probability. It's all about finding your sample space and then making your numerator what you need or what you're trying to accomplish.